Alright, in this video we're going to look at the negative binomial distribution. And again, we are going to start with identical independent Bernoulli trials. And remember that a Bernoulli trial is a trial where there are exactly two outcomes. We label one as success with probability P and the other as failure with probability 1 minus P. In this scenario, we're going to complete identical independent Bernoulli trials until we achieve R successes. Okay? Oops, I think I didn't spell that right. We achieve R successes. All right? So, for example, we might flip a coin until we achieve 3 heads. Or shoot a basket, assuming that every shot I have the same probability of making it, independent of shots that preceded it. Shoot a basket until I make 10 baskets. Okay? So we still have the same probability of success on every trial, P, but this time, and we have, instead of stopping on the last success like we did in the geometric distribution, we're going to stop after we have achieved R successes. Okay, we're going to let X count the number of trials needed to achieve R successes. Okay? R successes. Okay? Well, that means X can't take on 0, can't take on 1. In fact, the smallest it can be is R, right? I have to complete at least R trials if I want to stop at R successes. So it can take on any value with starting at R on forever. I could keep going for decades and not achieving 10 baskets, for example. Okay, so this is a discrete random variable because I can enumerate it, which means it sums, not integrals. All right, let's see if we can construct, since we have this random variable, we tend to care about the PMF since it's discrete. We are curious about the expected value and the variance of our random variable. All right, we are going to try to construct it based on the probability. So let's see. Let's start with our example again. Let's say we are going to flip a fair coin until we get 3 heads. So I recognize this is independent, identical Bernoulli trials where I get either heads or tails, and since I'm counting heads, heads are my successes, right? So the probability of success here, which we call P, is actually 1/2 because it's a fair coin, which means the probability of failure is also 1/2. Okay, so let's see if we can work it out. What if I say, what's the probability that it takes exactly 3 trials? Well, what does that actually mean? That means I get a success, then a success, then a success, which is 1/2 times 1/2 times 1/2, or 1/2 cubed. Let's see if we can generalize at the same time. Let's say it's not fair, or it's a different experiment and I don't have 1/2 as my P. What I really have is some P that's the same on every trial, so in this case it should be P cubed. Okay? Okay. All right, let's look at the case where x equals 4. So what does that actually mean? Well, I have 4 slots, and we know that we're going to have 3 successes in there, maybe there, there, and there, and the other one's going to be a failure. So we do know that we're going to have a success 3 times, and then a failure 1 time. Of course, that's the same as 1/2 to the 4th, but if we didn't know what p was, it's the same as p cubed times 1 minus p to the 1, right? But as we can see, there are many ways this can happen, and so we have to count the number of ways this can happen and then multiply it times the respective probability. We may be tempted to say, well, I have 4 slots and I want 3 of them to be S's, but that's actually not true. Because what that actually counts is this scenario, S, 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 in which case you would stop because we stop when we achieve the 3rd success. So this wouldn't fall into the 4 camp, it would fall into the 3 camp. So we really have this extra restriction that we just have to consider. We have 4 trials that it's taking, the last of which is our last success. All right? So the real question is how many ways can I put the other 2 successes in the 3 slots before the last? Okay? So 3 choose 2, p cubed to the 1 minus p. All right, let's do that again. We'll do it for, go to the next page. P equals to 5. Okay? What does that mean? It means it takes 5 trials in order to get 3 successes. What do we know? We know the last success is in the last trial. The other 2 successes can be anywhere in the preceding 4. That is, of the 4 preceding slots, choose where the other 2 successes go. How many S's do we have? That's our P cubed. It's always going to be cubed if our R is 3. And then we have the rest of the 5 as failures. Okay, let's see if we can set this up without actually writing out the chart. We know the last one has to be a success, which means the preceding 5 before the last, we pick the other 2 successes. We will have 3 successes because R is 3 in this case, and the remaining trials of the 6 are failures. Okay, let's see if we can do it for x equals to k. So that is, it takes k trials to achieve 3 successes. All right? So that means in the preceding k minus 1 trial, so the last trial is the last success, we choose the 2 other successes. We always have the 3 p's, but now we have the rest of the k that aren't the 3, so k minus 3, failures. Okay, let's super generalize. Let's say, let x be negative binomial. That is, the probability of success of each independent Bernoulli trial is p, but we're going to stop when we achieve r successes. Okay? And we want to write the PMF. We'll say the probability x equals x. That is, it takes x trials to achieve r successes. It's going to be of the preceding x minus 1. So remember, this is 6 trials of the preceding 5. It's 5 trials, it's the preceding 4. We're going to choose all the successes that aren't the last, so 1 less than the last. Okay? We are going to always have p to the r successes, because that's when we stop once we get that. And then the remainder of the x that aren't the r, so x minus r, are failures. So this is the PMF for the negative binomial.